Hello everyone, welcome to the next Eternity webinar episode. My name is Michael Zajda. I'm architect. I'm one of the tech leads in Eternity platform, and my background is in distributed systems mainly. And Eternity is very much distributed system. So I would like to tell you a little bit about my work. As I understand, you are able to ask me questions on the way, and I will. This is pre-recorded, so I will answer them as they come, and if I'm able to answer them. And the topic of the presentation today is evolution of the Eternity consensus engine, and I will try to focus only about it around it. I won't talk a lot about other future features or use cases of Eternity. We're gonna have next webinars. All right, so what's the consensus? Why it's important? It's pretty technical. It's, believe it or not, it's still one of the hardest problems in computer science. But I have this small plan to make it simple to understand and see how Eternity faces the problem of consensus and how it solves it. So I will tell you a little bit how we develop our software. I will tell you why consensus is important in the world of blockchains, how it affects its operations, and then I would like to compare and contrast a classic Bitcoin version with the protocol that we use. And to wrap it up in some meaningful way that give you a better grip on the topic, I will tell you about various consensus algorithms, which very often are not consensus algorithms. Another projects call them so, but it's a little bit more complex, and we will get to it. How to distinguish consensus from the whole engine around it, from the whole protocol, and how it affects the product, the platform. So yeah, this is a diagram I would like to use throughout the presentation to explain consensus and our protocol. What it is? That's a peer-to-peer network, which is heterogeneous. We see PCs, we see mobile clients, there is a small computing rack, big computing center and users around it. So here users submit transactions to the system, and even looking at this diagram will let you realize why we need consensus. Because of network delay or unstable network, each of those nodes has different view on the same transactions. You see, this is 3421 and this is 1342. So without consensus, without total ordering of those events, they are not usable. Maybe even on one host, on one network participant, on one system, they are valid, and on another, they are not, because ordering matters. If we send tokens or assets from A to B and deal with distributed environments, distributed networks, and by the way, all of that surfaced in the 70s when those networks started to be building. We need consensus when the data is rebuilt after unstable network or network split. So we need rules to establish what's the final state, how to build it, how to compute it, what's the final ordering of events that lead to current state. And what about blockchains? Does it apply to blockchains? Well, of course, the whole design behind the whole idea, Satoshi's idea, is the independence of blockchains, and they operate in distributed peer-to-peer network. We have the most pessimistic scenario for consensus. The network is dynamic. It may be full of malicious nodes. Each node of the network is in fact master node. So each of those nodes may emit events to the system and see its own ordering of truth. Right, and some of those nodes can omit some data. Some of them can replay data. Some of them can cheat and send false data. So these problems are the hardest to, and actually not solvable in pragmatic way by classic consensus algorithms. Think about something simplest, like the last write wins. So the last write to some record wins. If we have two users modifying the same database record, the second one is the one that wins and stays in the database. But in peer-to-peer network, there is no notion of time. We don't know which event came earlier, which came the second. So it's a little bit tricky, and this shows what a big breakthrough was Satoshi work. The Bitcoin consensus and the system around consensus, the engine around consensus to guard it and secure its finality, was the game changer. So let's dive into it. How Bitcoin guards consensus and what's one of the biggest dangers and solutions to that. Proof of work. If in our networks, if it's public, there may be some malicious nodes. They can affect consensus and rebuild it, so destroy it basically. So we need to make it as expensive as possible for them. And one of the solutions is proof of work. What is proof of work? It's a function that takes all the transactions it wants to confirm, that we want to confirm. It takes some metadata and random part. And the function computes value. And if the value meets certain conditions, we call it confirmed. We call it solved. And the block holding all the transactions we included in proof of work is called confirmed. And yeah, then this user, this miner who found the solution, who mined the block, who solved proof of work, he is he has the right to distribute the block throughout the network. And what happens if he didn't find? We applied those values and it doesn't meet conditions that are defined for configured for proof of work. Well, we change random part and try again and again. We may need to rebuild the block and try again. And finally, the lucky miner is the one to propose his version of the state, his version of the ordering that builds a state to the rest of the network. Why I called him lucky miner? Well, because we configure the protocol so it is very computationally heavy and it happens so rare that it happens so rare that it's, by the way, it happens every 10 minutes. So this guy needs to put a lot of computing power to solve the puzzle. Eventually, this happy guy here is representing the miner that solved the block. All right, what happens next? Next, we append the block to the chain of blocks. It's a linked list of blocks, and well, chain of blocks, blockchain, this is the name where it comes from. Here, where it comes from, here you can see it plainly. And what's the consensus algorithm behind it? How we decide what's the truth, what's the state in this gigantic network of chains. Maybe at some point we would have 2 miners, or some bigger block, smaller block. Some blocks came up earlier. How we decide what's the consensus? We choose the chain, the list of blocks which has highest difficulty, and the difficulty is a measure of effort put in mining the block. So the configuration of the protocol provides all the spec to do it right, and later it's validated by network participants. And to choose the current consensus, we choose the heaviest chain by difficulty. So simple, but so powerful. And one of the things we configure is 10-minute blockchain block time. So all the transactions are gathered in a block and applied to the proof of work function, and we wait. Expected mining solution time is 10 minutes at every point in the timeline. And it's incredible. It's incredible. It's a game changer. But is it perfect? Is it suitable for our current needs? Well, we find it a little bit hard with a number of use cases. For example, mobile devices, those beautiful, snappy interfaces. We would like to have more real-time feeling to it. So multi-minute block confirmation time is not exactly a thing that helps. And also, all those transactions, events in a system, they are accumulated and then secured by proof of work. I wonder if there is another way to keep the security, but make it lighter. Don't make it so CPU heavy. And you probably heard about it a number of times. The number of transactions a second in Bitcoin is very limited. It's like between 2 and 5, depending on conditions, a second. So it's comparing to some payment systems, it's orders of magnitude less. So how we can improve? How can we take it to the next one step further? Well, there is new hope. It's called Bitcoin NG. It comes from Cornell University researchers, and this is what we implemented in Eternity. And here I would like to tell you about 2 things. The title of the presentation is called Evolution of the Consensus Engine Eternity. Why we even need to evolve it? Eternity is written from scratch. We need to do so. We did so because we want to um, have operational blockchain from the very beginning. When we started work on current design, we decided to implement naive Bitcoin protocol. It took us about 2 sprints, and new team members, when we onboard them, could learn and see operational blockchain. So features and subsystems were implemented with the simplest algorithms, and then we improve them one by one. And the technology that we use, which is Erlang, also helps with that because it promotes isolation and component-based, service-based architecture. So this is why we even evolved this protocol around consensus. And how Bitcoin NG works? How is it better? Why we wanted to replace classic Bitcoin with that? Obviously, we are looking for latency improvements. We would like to take it from minutes level to seconds level. We don't want to make it real-time level because for that we have channels and stage channels. These are off-chain means of communication which are point-to-point, and they are perfect for that. So let's try Bitcoin NG. How it works, how it achieves this lower latency. Bitcoin NG introduces 2 types of blocks. Key blocks that are still guarded by proof of work and they choose temporary leaders, and microblocks that are only containers for transactions that are emitted by temporary leaders. And there is no proof of work in microblocks, so they are much lighter. The integrity is guarded by signature of the leader, but we will get into this. Yeah, there is one another take on that to compare with Bitcoin. When I do presentations about it, I like to name things differently to show you the difference between Bitcoin and Bitcoin NG. When you think about confirming a block in Bitcoin, you can think about the miner as the leader of events in the past. And in Bitcoin NG, miner is a leader of events in the future that will happen in the future. So Bitcoin NG pretty much reverses this approach. And let's see how it looks underneath. So again, we have proof of work. We have a solution of a block, which this time is key block. And the leader is dispatching much smaller microblocks to the network. Even now in this first slide, you can tell the difference because accumulated unconfirmed transaction list is much smaller. Mempool is much smaller than in classic Bitcoin because we don't accumulate this gigantic block before we can push it through the network. When we have elected leader, he has right to emit incoming transactions that are valid. He should pack them and sign them and broadcast as soon as possible with accordance to protocol configuration. So we have new chain format to follow that design. Key blocks, microblocks, and again key blocks by another leader. The height of the chain is incremented only on key blocks because this is where the difficulty happens. This is where we apply proof of work. And microblocks inherit height from the key block. So the public key is held in a key block, and microblocks are signed with corresponding private key to this public key that is known to everyone after the key block is broadcasted throughout the network. And all of that happens until proof of work chooses, or the new miner mines a new key block. Then we switch the leader and there is new key pair to maintain a microblock subchain. So there is an interesting challenge in this scheme, because how to make the new leader follow as many microblocks as possible, how to motivate him to do so. And there is really interesting and neat solution to that. It's a fee split. So as in Bitcoin, leaders get Coinbase transaction, the Coinbase award, basically award for mining, but also they get fees from the transactions that happen in their generation, we call it. If we split those fees 40 to 60%, 60% goes to the new leader. His incentive is to include as many microblocks emitted by the previous leader in this generation. So in his best interest is to follow as many microblocks as possible and include them. We are also investigating another values here, but this pretty neatly guarantees, well, motivates network participants to behave well and follow the protocol. Still, even if everyone is behaving well, due to network propagation delay, there are possible microforks. And this is all fine if the transaction 5 and 6, or those two events, happen also here, but the next leader followed the chain at the third microblock. As you see, this is all fine. He simply repacks and resigns those events in the first microblock, not in the first, in any microblock that he emits, any he likes. And also when he's solving the block and he's emitting next or the first microblock, it's very likely that the diff between his first microblock and those omitted microblocks is very small, because mempools tend to be similar. So the diff to reconcile later on is, first of all, not so big, and then easy to do because microblocks are very cheap operation. So what's the configuration of our protocol? We want to let leaders emit microblocks every 3 seconds, and we will tune our proof of work algorithm to 3 minutes to elect a new leader. And this will give us this latency that goes well with apps that we want to create. It's still, as you see, it's still not real time. Furthermore, this is very, very optimistic, even theoretical latency, because we need to include network latency, which can reach couple. It's a game changer comparing to multi-minute platforms like Bitcoin. Yeah, and what can happen more? Probably a whole bunch of you ask question, what if the leader is malicious? What he's doing some bad stuff? Well, there is a mechanism to disincentivize leaders from cheating. Because what can malicious leader do? He can omit transactions. He can reorder them. That's pretty hard to punish because it can happen only even in current systems, even in Bitcoin. But what we want to discourage is double spend. Imagine that a malicious leader emits a micro fork with the same spending money from the same accounts. So those events here, they double spend some assets, some tokens. So how to deal with that? Our take on that, and suggested formulated by Bitcoin NG designers, is to use proof of fraud. So the proof of work will reconcile which chain of events is the right one, which will form the state. So it will never happen that two of them are included, because one of them will not be validated by parts of the network. So one or another. And proof of work will tell you which is the correct. But still, we want to punish previous leader to incentivize good behavior, not the bad one. And pretty quickly, when network syncs, it's going to be obvious that previous leader emitted a microfork. So if we detect that two microblocks had the same parent, we will issue proof of fraud. These will be two headers, and we don't get into details. What operation was it double spent or not? If there is this condition for double spent, like microfork, we publish proof of fraud, and the consequences that we take away Coinbase award and fees awards from the previous leader. So he put all the effort and all the computation to become a leader, and he will get no reward for that. Those blocks, malicious blocks, are discarded by the network as invalid. And of course, for a brief time in network operations, some nodes could read them as valid, but again, we inherit all the security guarantees from Bitcoin. And as we know from Bitcoin, it's good to wait for a couple blocks confirmations to be sure that we are on the main chain, that it's not a fork. So it's the same. The same holds here. All right, so let's sum it up. What are Bitcoin NG benefits? We take transaction confirmation time down to a level of seconds. We splitted a proof of work application to two types of blocks, and we make only choosing leaders computationally heavy. We make dispatching transactions through the network cheap and efficient. And thanks to that, we can increase transaction throughput in the network. You can start at 100 transactions a second, and we have ways to improve it. So yeah, I think it's a step in the right direction. And it's still a framework that let us build on the top of that. We can improve from here with sharding or with another solutions to malicious miners, like some sort of quorum or BBBFT on the top. So I hope you see differences and advantages of one another of Bitcoin NG comparing to the classic Bitcoin from the beginning of the presentation. Oh yeah, and let's wrap the presentation with another consensus algorithms or protocols around consensus. The first bullet point says Paxos and Raft. These are very classic ones that are applicable in private deployments in very stable and networks of well-connected hosts. They would not be practical to use in dynamic networks with potentially malicious participants. It would take a lot of time, and maybe it wouldn't be even feasible to achieve consensus. This is why proof of work was such a breakthrough. And there are still another systems the basing of proof of work. In this blockchain world, like the opposing pole is proof of stake to proof of work. But this is actually pretty funny because it's the same consensus underneath, and these are just two ways of preventing from Sybil attacks. And as a matter of fact, proof of work is also proof of stake. Just the stake is the amount of effort we put into computing new block. So they're very, very similar. And I have this feeling that they are shown us something completely different from technical point of view. So I think it's not correct. From technical point of view, these are actually, there are similarities. They are actually different from product point of view, because in proof of work, we promote users with high computing power, and in proof of stake, we promote users who own the biggest stakes of tokens, which affects your product. There is later on there is delegated proof of stake. I jumped to it. It has similar name, but it's completely different. It's about delegating your right to decide on what's consensus. So it forms a chain of delegation and a group of users that got votes or this right from another participants of the system can choose consensus. But again, look how it's similar to classic one. There is still this, it may be the same structure underneath. It may be the same linked list of blocks. Simply the mechanism around it to guard its security is slightly different. And how deceiving it is, the naming, is the proof authority. I think it's a good example, because proof of authority is not that different from permissioned network, even controlled by a single entity. Proof of authority is basically one node or some group of nodes controlled by third party that has authority, and it chooses consensus, chooses this current state. So it's simply master node owned by third party. Proof of reputation may be something based on reputation. At the end of the day, we may not control all the conditions to choose this entity, and it's again some third party deciding on consensus. Okay, so it's another thing. To follow up on the different options, proof of elapsed time. Again, something suitable for private closed networks. Because why we need to spend this whole computational effort if we can use simply function sleep and sleep for a random amount of time, who wakes up? He decides on consensus. Well, of course, it's not applicable in hostile environment of nodes, of malicious nodes. So it's good for private networks. Proof of weight. It's another kind of proof of stake approach. Simply the stake is some sort of capacity, some sort of weight. It seems to be useful, or seems to be mapping well to archiving blockchains, where the highest power may be given to nodes that hold the most memory or the most storage. So this is why it's called proof of weight. But again, I think it's not that far from proof of stake. And the last dot is, I think, the most interesting. It changes a little bit more. It changes also the structure that consensus is built on. So it's not longer a linked list, but something else. And in the three first diagonal spectra, it's diagonal directed acyclic graph. So it's not longer the special case of a list, but it may be more complex. And it actually allows interesting use cases. It may reduce event submission time, latency, to very low values. However, usually we know about consensus and the final state when we read it. So it's not a write-time consensus, but read-time consensus. So what else? Lattice. It's a chain of blocks per each user. So any event has to update 2 chains. Well, also interesting scheme to guard state. Recently, it gets more popular, voting. So why don't you use voting to establish which transaction is valid and which is not valid? So there are at least two projects using that approach. And why even group transactions in blocks? Originally, it was designed to make the network synchronous, providing the solution time is higher than the network propagation time. The network becomes synchronous. But maybe we don't need those big bulk sets of transactions. So maybe blockless is blockless approach, building structures, data structures out of pure transactions will be just fine. So yeah, these are completely new approaches to engine around consensus, data structure, and communication in peer-to-peer network. It's probably too early to tell which will fit public networks, because this is the question. They work great in less hostile environments, in permission deployments, but yeah, they may show us some new ideas to follow and improve. All right, this is it. Thank you. It was great to have you in this webinar, and thanks for listening. I hope in the background I answered your questions. Thanks.